Continuing downward into the Earth, we reach the transition zone from around 400 kilometers depth to about 660 kilometers depth, where we have a slow change in properties, most likely accompanied with a slow change in mineralogy. At about 660 kilometers, we see S-wave velocities increasing abruptly. This is almost certainly due to a change in chemistry and the associated change in mineralogy. Moving further down, this is where we reach the lower mantle below the transition zone, where S-wave velocities increase for the next 2,000 kilometers with depth. Ultimately, we're going to reach the core mantle boundary at 2,900 kilometers depth. And here at the core mantle boundary, we see a very dramatic change from solid silicate rock, predominantly, to a liquid iron alloy. The complete loss of rigidity at this boundary reduces the S-wave velocity from 7.5 kilometers per second to 0. And that's because S-waves cannot travel through a liquid. We also see the P-wave velocity change. In this case, it goes from about 13 kilometers a second to around 8 kilometers a second. And this ultimately results in the formation or generation of the core shadow zones. Associated with this phase change from a solid to a liquid, the chemical change results in a dramatic, large increase in density. This density increases by about 4 grams per centimeter cubed. When looking at the Earth's internal temperature, we have to consider how heat moves through the Earth's interior. It can move via conduction through the lithosphere, the solid Earth surface, or it can move by convection in the mantle and core, where there's some movement of material. Again, in the lithosphere, in the crust, there's no significant movement of material, whereas the convection in the mantle and core allow for substantial movement of material and therefore transfer of heat, much like the ocean transfers heat from low latitudes to high latitudes, and the atmosphere transfers heat from the Earth's surface to higher altitudes and higher latitudes. When we take a look at a cross-section of the Earth, the dynamic movement of the interior of the Earth becomes apparent. Here we can see the convection of hot material from deep within the Earth, making its way to the surface where it's forming a new crust. This new crust is hot, it's buoyant. As it ages and cools, it becomes denser. As it becomes denser, it sinks. As it sinks, it may be assimilated chemically into that portion of the mantle, or it may end up in a slab graveyard. We can see a mini example of this looking at a lava lake. The cooling of the lava, the spreading out of the crust, represents a mid-ocean ridge here, potentially. As this material moves away from the spreading center, it cools off. As it cools off, it becomes more dense and it sinks. In the mid-ocean ridges, both in the Atlantic and in the Pacific, we see an initial increase in temperature and a subsequent bulging of that material. The hot material takes up more space, therefore it's less dense. It expands. It rises, it floats. The rate at which a mid-ocean ridge is created is therefore going to determine the volume of the mid-ocean ridge. The faster this material is generated, the larger the volume. The larger the volume of the mid-ocean ridge, the more displacement of seawater. So when ridges are being produced quickly, sea level tends to rise. When we look at the Earth's internal temperature, from the surface to the center of the Earth, we see a series of changes associated with changes in, again, phase and mineralogy and therefore chemistry. The yellow line here represents the geotherm, the temperature within the Earth. And you see that temperature rising as we go lower into the Earth. But it doesn't rise steadily. It rises very dramatically within the lithosphere as we go from the surface, where it's quite cool, the Earth's surface that we walk on. As we get down lower into that crust, temperatures rise as we get closer to the heat source below. So we'll see a transition here. We're looking now at the temperature of the Earth compared to the melting curve of the Earth. This is the temperature at which rock would melt. When this temperature is to the left of this temperature, or this curve is to the left of this curve, we have molten material. So we see that here near the surface. This mantle melting curve generates the low velocity zone. This low velocity zone is the result of some liquid being present in this layer. That quickly goes away. And by the time we get to 400 or so kilometers depth, the geotherm is well to the left of the melting curve. And as a result, this is a solid silicate rock in this portion of the mantle. When we reach the base of the mantle, we see temperatures rise again very dramatically. We also see a transition from a solid to a liquid. So we go to the left of the geotherm again with the mantle melting curve, and that means that this material is liquid. So we have a liquid from here, around 2,900 kilometers depth, to a little over 5,000 kilometers depth. And then we transition again such that the mantle melting curve is to the right of the geotherm, and therefore we're in the solid iron alloy section of the Earth's interior. Normally, this geothermal gradient is about 20 to 30 degrees centigrade per kilometer increase in depth. This means we can see it in some of our deeper mines. Some of the gold mines in South Africa, for instance, are very, very hot at the bottom and have to be air conditioned for people to stay alive, basically, while they're working in these mines. By the time we get to the base of the lithosphere, we're well beyond the capacity for human life. We're at 1,300 to 1,400 degrees centigrade. And then beyond that, as we enter the core, temperatures rise from 3,000 to more than 6,000 degrees centigrade at the center of the Earth. When we look at a cross-section of the Earth in 3D, using what's called seismic tomography, we can see things within the Earth that aren't visible from the surface. So here, the types of things we would observe in a tomographic cross-section include hot areas or hot regions, such as a superplume rising from the Earth's core beneath South Africa. So this superplume is responsible for the mineral wealth of South Africa. We have a similar plume beneath Wyoming in the United States. So we can see that via tomography, seismic tomography, which models the speed at which seismic waves travel through the Earth's interior, therefore telling us about its density and about its rigidity. The Earth's gravity field tells a similar story in that the change in density induces a change in gravity. The denser a substance, the greater the gravitational pull per unit volume of that substance. And lastly, we can take a look at the geoid, the actual shape of the Earth. Before we move on to that, one last thing to get out of this is that it's believed some of these cooler regions represent descending plates. The plates of plate tectonics, as they descend into the mantle, they cool off. But they're very large masses, so they cool off slowly, and they also pull heat from the surrounding warmer regions. The net result is we can see, at least we think we can see, these cold slabs, these cold chunks of former superficial crust sliding down into the mantle, where they may get stacked up in what's known as a mantle slab graveyard. Taking a look at the Earth at 4 different depths, near the Earth's surface, the cool areas, the cool regions within the Earth, look similar to the continents. So here we can see South America, North America, we can see Asia, we can see Africa here as cool features in the Earth at 70 kilometers depth. When we move to 200 kilometers depth, we still see those large cool regions that are related to the continents. At about 500 kilometers depth, things start to get a little bit different. We still see this coolness beneath South America, but it's not so cool beneath North America. So we lose the feel for this continental crust at 500 kilometers depth. And then near the core mantle boundary, all bets are off. We don't see the continents clearly anymore. What we may see are those graveyards of lithospheric slabs, these slab graveyard. The geoid, the shape of the Earth, is going to be related to what's going on within the Earth in terms of its gravitational pull. And we can see that the observed geoid, the shape of the Earth, looks pretty similar to what we would expect based on mantle convection, based on the cycling and recycling of cold and hot material. When we look at the magnetic field and the geodynamo as observed by simple instruments at the surface of the Earth, like a compass, we can begin to see there's a complexity that we have to take into account for communications, for navigation. This is the non-dipole field component. A dipole, it means two poles, and it's essentially what you would get if you had a bar magnet. A bar magnet sitting in a field of iron filings gives us our common high school or even grade school depiction of how a magnetic field works. So in very simplest terms, that's the dipole. We do have, because of the circulation within the mantle and the core, some complexity that goes beyond a simple dipole field component. That's the non-dipole field component. We also see secular variability in the field. This variation in the Earth's magnetic field is something we can observe, again, using a compass, something very simple. The changes in the field are going to be faster for the non-dipole components. The subtle variations in the circulation of the core, the actual shape of the outer core, the tomography, the bumps in that core are going to play a role in what's observed at the Earth's surface in terms of the magnetic field. We also run a tremendous risk, ultimately, when we have a magnetic reversal. This is when the Earth's magnetic field flips. So our north magnetic pole flips to become our south magnetic pole. And that's not a smooth transition, as we'll see in a minute. When we're looking at the position of the north magnetic pole, again, this is something you would pick up on a compass, we observe that that position has changed substantially over the last 400 years. Starting about 400 years ago, the north magnetic pole would have been located about here, north of the Canadian Arctic Islands. Since then, it cruised to the south from 1600 to 1700. Now it's in the Arctic Islands. 1800 still in the Arctic Islands. 1900 again in the Arctic Islands of Canada, but moving east. And then we move north in 100 years, the last 100 years, up to a location here, north of Axel Heiberg Island. So we're close to the North Pole, but still, a couple hundred kilometers away. Now, it essentially appears like this. Here we have a dipole tilted by 11 degrees, as we observe in the modern world. Was it always this way? No. So here we have the surface as mapped in the year 2000, about 20 years ago. If we look back a little further to 1900, the magnetic field mapped at the core mantle boundary starts to look different. We see some differences between this and this, particularly the magnetic component here becoming much, much stronger in the year 2000 compared to 1900. And if we go back a little further to 1800, we don't see that anomaly at all. If we do, it's off to the west here, moving towards the east. So these are changes that occur at a very rapid rate in even human terms, but certainly in geologic terms, basically an instant. So what does this look like in terms of the magnetic field lines? Here we have field lines that represent the Earth's dipole. So the North Pole here, South Pole here. These magnetic field lines are going to extend well beyond the Earth and then curve back around like so. The field lines over here are going to cruise off this way, curve around like so. Now, this is the modern simulation of the magnetic field lines of the Earth. When there's a reversal, we'll start out with step 1 here. We see magnetic lines with normal orientation. This is what we observe today. The magnetic lines of force are going to approximate those of the dipole field. So these field lines are going to represent the magnetic field. Essentially, that's what that means. Now, we're starting to see a magnetic reversal here. So the magnetic pole is drifting away from the rotational or geographic North Pole here. It's getting further away. These field lines are getting more and more twisted, crazier looking, continuing on, even crazier looking magnetic field lines here. And then as the reversal is completing, we see the South Pole field lines now emerging from the northern portion of the Earth and the North Pole field lines coming from the southern latitudes of the Earth. So this is something that does happen. and we should care about it. The question is, why should we care about this? Well, the Earth's magnetic field protects us from the sun. It gives life and it takes life away. Higher frequency energy is dangerous to us. X-rays, gamma rays, cosmic rays, ultraviolet light, those are ionizing radiation, or those are forms of ionizing radiation. That does damage to our genetic code. We can get skin cancer. We can get destroyed by this high energy radiation. And when the Earth's magnetic field reverses, we lose this protective shield. It goes away. So for some period of time, and we don't know how long that period is, the Earth is left vulnerable to being bombarded by high frequency, short wavelength radiation coming from the sun. We're exposed, much like an astronaut is exposed in space, which is why they wear another reason they wear special clothing. This magnetic field of the Earth is kind of like Iron Man's shield. I've never seen this movie, but it's kind of like that. So what can we use this magnetic field for? There are some uses, very interesting, very important uses. One of which is Paleomagnetism, the ancient or old magnetism of the Earth. This records the magnetization of the Earth, and therefore it records the magnetic field in the Earth's past. This can be used as a thermoremnant, a heat-generated magnetic signal that's stored in a rock. We can have a depositional remnant where magnetic particles align themselves with the Earth's magnetic field. As they're lithified, they preserve that magnetic field in those rock layers. And we can use this magnetic stratigraphy. This is a cheap way to determine the age of a rock. The thermoremnant record here, or example here, takes us to Central Australia. This is a place called Uluru. Later on, it was named Ayers Rock. These are Aboriginals building a fire 30,000 years ago. If these rocks are not moved between 30,000 years ago and today, they're found by archaeologists in place, or pointed out by the Aboriginals that still live in the same region, on the same land. Those rocks were heated beyond what's called the Curie point. And at that Curie point, the magnetic field that the rocks are exposed to is going to be preserved in that rock. When it cools down below that Curie point, it locks in that signal. So some geeks can come along today with some compasses and measure the magnetic field in this rock, and the difference between the magnetic field in the rock measured today and when the rock passed that Curie point 30,000 years ago will tell us the difference between the Earth's magnetic field today and the Earth's magnetic field 30,000 years ago. In a similar situation, but totally natural here, magnetic mineral grains are deposited on the floor of a lake or an ocean, bog, anywhere there are magnetic materials, magnetic minerals that are settling. Those are going to tend to align themselves with the contemporary magnetic field of the Earth. Once these grains are lithified, locked together, they're going to preserve that magnetic field for that time. And then we get into our money-saving aspect here, the Paleomag timescale. This is basically a depiction, a tape of the polarization of the Earth. When the Earth's north magnetic pole is in the north, or the north magnetic pole is in the south. That's the black and white bands here, much like a barcode in a store. They're going to record this positive, negative, positive, negative, positive, negative variability. So every time we see a change in color here, that represents a magnetic reversal, and that represents a time when the Earth was exposed to dangerous amounts of ionizing radiation. There are a couple periods of Earth history, in particular the Cretaceous Quiet Zone, where we don't see evidence of magnetic reversals for a very, very long time. We don't quite understand why this happened. We don't quite understand why we get into periods of time where there are lots of rapid reversals. It might be that these periods of rapid reversals lead to enhanced evolution and extinction. So a lot more pressure put on the biological world to make changes, to adjust to the damage that's done during a reversal and recover by introducing new species of plants and animals. This magnetic field has important implications for animals today. It's believed that birds can detect this magnetic field. They see the magnetism of the Earth, and it's thought that this view of the magnetic field of the Earth allows birds to migrate long distances, in some cases 10, 15, even 20,000 kilometers of migration. It's believed that's being done along the Earth's magnetic field lines. Now, what happens in a reversal? I don't know. That might be the end of that particular species of bird. So we see the magnetic field, and the biosphere sees the magnetic field and uses that magnetic field in a way that's similar to the way we use it. We use it for navigation, and so do the animals.